In this video, we're going to look at some properties of definite integrals. Let's start with the theorem. If f of x is continuous on a closed interval ab, or if f of x has only a finite number of jump discontinuities, then f of x is integrable on a closed interval ab. Therefore, the definite integral a to b f of x dx exists. As an example, here we have an integrable function, piecewise continuous, and you can see that we've labeled the parts of the curve that are above the x-axis by a1, a3, and a5, and the parts of the curve below the x-axis, those areas are labeled a2 and a4. The net area is going to be a1 minus a2 plus a3 minus a4 plus a5. So let's write that down. We have integral from a to b f of x dx, that's the net area. Integral from a to b f of x dx, that's equal to a1 minus a2 plus a3 minus a4 plus a5. So all the areas that were below the x-axis were subtracted. All the areas that were above the x-axis were added up. Let's look at another theorem. If f of x is integrable on ab, then the integral from a to b f of x dx is equal to limit n goes to infinity, I goes from 1 to n, f of xi delta x. That's equal to limit n goes to infinity, I goes from 1 to n, f of a plus I delta x times delta x, where delta x is equal to b minus a over n. Xi, the x values, is a plus I delta x. That's equal to a plus I times b minus a over n. This part here is the Riemann sum. This is the right-hand point. When we take the limit of this right-hand point, we get a definite integral a to b f of x dx. All right, the definite integral is a number, so it doesn't matter which variable of integration you use. The integral from a to b f of x dx is equal to integral from a to b f of t dt is equal to integral from a to b f of u du. All right, let's look at some properties of definite integrals. Property 1, integral from b to a f of x dx. This is equal to minus integral from a to b f of x dx. So if you interchange the limits of integration, you have to put a minus sign in the front. Let's look at an example. Integral from 2 to 1 x squared plus x dx. This is equal to minus integral from 1 to 2 x squared plus x dx. Property number 2, the integral from a to a f of x dx is equal to 0. As an example, integral from 1 to 1 sine of x squared dx is equal to 0. And the reason for this is because we just have a vertical line, and a vertical line is not going to have any area. So the integral is 0. So here is a, and here's f of x. And the dx is actually 0 because there's no width. So for this reason, the integral is going to be equal to 0. All right, let's look at property number 3. Here we have integral from a to b c dx is equal to c times b minus a. Let's illustrate with a diagram. So what we have is, here's the y-axis, here's the x-axis, and we're integrating from a to b. The function has a height of c. So here's c, this is y equals c, and the width is b minus a from here to here, from a to b. So the shaded area is going to be the area of this rectangle, which is c times b minus a. Let's shade that in. So this is the shaded area. All right, let's look at property number 4. Here we have integral of a sum is sum of the integrals. F of x, so integral of f of x plus g of x dx is equal to integral from a to b of f of x dx plus integral from a to b of g of x dx. Let's give an example. Integral from 1 to 2 x cubed plus x squared dx. That's equal to the integral from 1 to 2 x cubed dx plus integral from 1 to 2 x squared dx. Integral of a sum is sum of the integrals. Property 5. Integral from a to b c f of x dx. The constant passes right through the integral. So we get c integral a to b f of x dx. C is any constant. So C is a constant. All right, so let's give an example of that. Integral from negative pi over 2 to pi over 2 4x cos x dx. 4 is a constant. It passes through the integral. So we bring it out. That's 4 integral from negative pi over 2 to pi over 2 x cos x dx. Property number 6. Integral from a to b c1 f of x dx plus c2 g of x dx is going to be equal to c1 passes through the integral, so you get c1 a to b f of x dx plus c2 integral from a to b g of x dx. All right, let's give an example of that. So what we have is integral from 0 to 1 to e to the x plus 3 sine x dx. That's going to be equal to integral from 0 to 1 to e to the x dx plus integral from 0 to 1, 3 sine x dx. But these constants pass through the integral. The 2 passes through the integral and the 3 passes through the integral. So we're going to get 2 times integral from 0 to 1 e to the x dx plus 3 times integral from 0 to 1 sine x dx. All right, let's look at property number 7. Here we have integral from a to c f of x dx plus integral from c to b f of x dx is equal to integral from a to b f of x dx. Let's illustrate this with a diagram. So here we have the y-axis, and here we have the x-axis, and we have a, c, and b, and some arbitrary curve. So this portion here is the integral from a to c f of x dx. That's a definite integral. And this shaded area is the integral from c to b f of x dx. So it's clear that if we add these two, we get the entire area from a to b f of x dx. All right, so now let's look at property number 8. Property 8 is actually quite easy. It says that if a function is positive, if f of x is larger than 0 for x between b and a, then the integral, the definite integral, a to b f of x dx, will be larger than 0. Let's illustrate this with a diagram. So we have a function from a to b. And you can see how, if you look at one of these slices, here's f of x, and here's the width dx. F of x is positive, dx is also positive. So we're going to have a positive area. We're basically adding up all these rectangles. So what we have is, if we look at the slice separately, here's f of x, here's dx, and the differential area, dA, is f of x dx. This differential area is positive. If you add up all these areas from a to b dA, that's going to give us the whole area, which is larger than 0. And by adding up these slices, what we really mean is all of these rectangles. So this one here and all the ones in between. And I guess that's what the Riemann sum was doing before. All right, so that's something that we expect. If a function is positive, then the area a to b f of x dx, which is the area under y equals f of x, is also positive. Let's look at property 9. Here we have, if f of x is larger than g of x for x between b and a, then the area under f of x should be larger than the area under g of x. A to b, g of x dx. Let's illustrate this with a diagram. So here we have y is equal to f of x. That's the top function. We have the bottom function, y equals g of x. And the interval is from a to b. Those are the x values, the endpoints. That's the x-axis. Y-axis, this is the origin. So you can see how the area under g of x is this part here. The area under f of x is all of this. And it's clear that the area under f of x is bigger than the area under g of x, because every slice, if you look at every one of these slices, the area of the slice under f of x is bigger than the area of the slice under g of x. If I was to draw this with a diagram, f of x dx would be like f of x dx. That's the area of the slice under f of x. And the area under g of x would be much smaller. So that's g of x dx. All right. So now let's look at property 10. Property 10 says that if the function f of x is less than capital M and larger than small m. Capital M is the absolute value of the function f of x on the interval a, b. And this property says that the integral a to b f of x dx is going to be less than the area of the larger rectangle, which is capital M, from here to here is capital M, times b minus a, and from here to here is b minus a. And it is larger than the smaller rectangle, which is small m times b minus a. So we have a proof here. So basically, the f of x is bounded between capital M and small m on this interval. Now you integrate the whole thing, integrate everything in this inequality. So the integral a to b m dx is less than the integral a to b f of x dx is less than integral m dx. But we already know that this integral, this definite integral from an earlier property that we looked at, is just small m times b minus a. And this integral here, integral m dx, is just the area of a rectangle. That's capital M times b minus a. So we have a way of estimating integrals. And in the next video, we're going to look at that and do some estimations. All right, thank you. Let's clarify property 10 a little bit more. F of x is less than or equal to capital M and larger or equal to small m. Capital M is the absolute maximum of the function f of x on the interval a to b. Small m is the absolute minimum of the function f of x on ab. That means capital M is the highest y value on this interval ab, and small m is the lowest y value, the smallest y value, the absolute minimum of the function on the interval a to b. All right, thanks.